We provide existing models with our package, but what if they don't correspond to your design? As we mentioned earlier, in that case, you could just create your own component models and import them into the global ones. This is what we're going to explain now. The design cycle for most of the wind turbine manufacturers probably looks like this. We start from a model of the machine and use it to compute loads acting on the different components. These loads can then be considered to be specifications for the component designers. They will then perform their own design using some detailed local analyses with tools like SAMSEF4 wind turbines FEA or SAMSEF4 wind turbines gearboxes. Once they come up with a design better suited to their global needs, this new design should be reintegrated into the global models, and new loads should be computed to check that the ones used on the specification list are still valid. This last step is unfortunately not always easy, because it requires the usage of a software package into which new components can be imported and used, and not just replaced by some equivalent properties, changing the global picture only slightly. The way to build new components using our tools is explained in other chapters on this DVD. As shown there, our component design GUI, SAMSEF Field, is most often the tool used for that purpose. There are two major cases why users would use this tool. First, if the user wants to design and test a new, very different concept from the pre-embedded ones, like a bed plate with a specific shape, or a gearbox with 4 stages. Secondly, a missing feature in the pre-embedded model corresponding to the desired design is also a reason to create a new model. When creating new components, it might happen that what we call the wind turbine topology, that is, the way the components are placed with respect to each other and the way they're connected, is different from what exists by default. In that case, we need a tool to still be able to connect the new components with the existing ones. Let's see how easily this can be achieved. To do so, we'll use the example of a new bed plate that was already reduced to a super element. Retained nodes of this super element correspond to the ones that will be used when connecting the bed plate to the tower and the drivetrain. What we need to do here is to make sure that when defining this model as the one used for the bed plate in the global model, SAMSEF4 wind turbines will be able to build this global model in one piece and not have the bed plate remain independent from the rest. Achieving this is very simple. Every connection point should be given a name via a tool called selections. For example, we can define the node through which the second main bearing will be attached to the bed plate. The same is then done for each relevant node. You can see that there are even nodes foreseen for a nacelle, even though we have seen that there is no such component by default. And that is all that's needed on the SAMSEF field level. Let's now see what should be done on the SAMSEF4 wind turbines GUI level. First, we have to replace the existing bed plate by the one we intend to use. If you recall, there were a few mysterious items in the list of models shown earlier. We're going to use them now. So let's pick SAMSEF field model for the new bed plate. After defining the path to the corresponding model, we go and check the so-called connection table. This table is made of the connectors listed by pairs. Each component has its own set of default names, but they can, of course, be edited. New pairs can also be defined if needed. The orange items you see correspond to connectors that are not located on the same spot. This happens if the new design dimensions do not correspond to those belonging to the rest of the structure. This means that most likely slight design changes will also be needed on other components. In our case, the torque arms of the gearbox are higher than their connectors on the bed plate, so this should be modified. This is easily done, and the table shows that everything is now perfectly coherent. The view can then be updated, and the new bed plate model is properly represented in the global model, so long as its CAD model can be accessed. So let's sum up the advantages of the openness of our tool to new components. First of all, it makes little difference to SAMSEF4 wind turbines whether the new component is a structural or a mechanical one, since connections are defined in the same way. In the case of structural components, you can use either full finite element models or reduced ones. If needed, You can simply remove one or several components, for example, in the case of a direct drive turbine. On the other hand, the user can also add components that do not exist in the default model, like a nacelle box. Just define the connection table for this new component, as well as for new connectors on the component linked to it. As a consequence, defining an offshore model in our package only requires using a new component for the tower, taking the waves and the foundation into account, but everything else remains the same. Any foundation type, from a tripod to a floating platform, can then be added to the tower model, or underneath it even, as a new component. Now that you have seen some of the possibilities with this tool, it's time to draw the conclusions of this presentation. We've clearly seen that SAMSA 4 wind turbines' structural dynamics is a must to be able to represent real loads with a high level of accuracy. Thanks to that, real durability information can be obtained so that the turbines designed are much more reliable. Your own design can be modeled easily and accurately thanks to the considerable openness of our software package. Thanks to all that, a large amount of money will be saved on maintenance and warranty, and, equally important, the satisfaction of your customers will increase because the downtime of the machines they buy will be drastically reduced.